Okay, so if you're watching on video, go ahead and push pause and do the basic rational functions review. See if you can make these graphs from memory. And so here we go. So the first one's the reciprocal function. Now, if you needed to draw out the table, that is totally fine. I have no problem with you doing whatever side work that you need to do. But remember, all that's happening is whatever x value I plug in, this function is saying make the reciprocal of it. So when I put in 2, the reciprocal of 2, 1 over 2 is 0.5 or a half. When I put in 1, the reciprocal of 1 is 1. When I put in a half, reciprocal of a half is 2 when I flip that fraction. Then we saw when we did this, and we also see here that when I put 0 in, 0 has no reciprocal. We can't divide by 0. So I draw a vertical asymptote right here, right down the middle, a nice dotted line. Graphs never go through the vertical asymptote. Okay, I tried to make a big deal of that last time. Hopefully it was memorable. And also on this graph, since there's a 1 in the numerator will never be 0. So this graph never goes through the y value 0. So I'm going to draw a horizontal asymptote right here. And so this is the graph that's on the right side. I'm not going to overextend it because I don't want it to merge into the x or y axis accidentally. To the left, same sort of thing. When I put in -1/2, I get -2. That's the reciprocal. When I put in -1, -1 is the reciprocal. And when I put in -2, 1 over -2 is -0.5. That's my reciprocal. Remember, our asymptotes define the behavior of the graph, so it's never going to go through those asymptotes. So that is a lovely little sketch of 1 over x. Okay. Anything that you didn't remember, anything you're confused about there? Okay, I didn't put any transformations on this just for time's sake, because section 5.2 has a lot of time, but when we warm up next class, that might be part of what we do. Okay, now what we're doing is the same sort of thing. We're doing the reciprocal again, but now we're squaring. Okay, so it's the reciprocal square. So when I put in 2 this time, 2 squared is 4, so 1 over 4, so 1/4. When I put in 1, 1 squared is 1, so the reciprocal of that is 1. When I put in a half squared is a 4th, and when I do the reciprocal, that is 4. So there's my graph. The same things are true here as were true for the reciprocal function. I've got a vertical asymptote of the axis because there's no reciprocal of 0. And since the numerator of this is 1, I'm never going to get the y value 0 out. So this is a horizontal asymptote. I'm just trying to draw those without messing up the rest of the graph. So this just basically looks like a stretched out version of the previous graph. And then on the left side, because we're squaring, we end up with an even function. So -1/2 when I square it is +1/4, and the reciprocal is 4. -1 squared is 1, the reciprocal is 1. And -2 squared is +4, the reciprocal is 1 over 4, so this. So again, you get a stretched out version of the previous graph, but this time it's above the x-axis. So there's my 2 new basic functions that we began talking about last time. So please make sure you're familiar with them. Make sure you can do the translations and stretching and shrinking. There will be a little of that on the next test. Now, before I do the great big reveal, we started section 5.2. We did one little bit of the 5.2 sheet that I know is in front of you. We talked about vertical asymptotes, which we'll bring up again later in the section. When do vertical asymptotes happen? Well said. When the denominator's 0. So just to bring you up to speed, in case you were not here, this is on the video that was already posted. For these 5 examples, we found the vertical asymptotes. Vertical asymptotes always occur when the denominator is equal to 0. You can't divide by 0, so that puts up a force field in our graph of our rational function, and these were the vertical asymptotes we've got. Because asymptotes define the behavior of the graph, when we go to graph rational functions, the best information we are going to have are the vertical and the horizontal asymptotes. So we found vertical ones. So next thing is horizontal asymptotes. So I've got 6 examples. I'm going to do 2. You're going to do the other 4 of horizontal asymptotes. Now, When do horizontal asymptotes occur? Well, that's a great question. I haven't told you yet, so I'm not expecting an answer. There are two situations you are going to find out about in this class. So I'm going to just go over to the side over here. I didn't really do a good job typing up this sheet. There are two possibilities. Okay. So this is for the horizontal asymptotes. I'm just kind of doing it over on the side where I have a little room to write. There are two possibilities for horizontal asymptotes. Possibility one. Possibility one is when the degree of the denominator, in case you don't remember what the degree is, okay, that's something probably you learned in introductory algebra. The degree, meaning the highest power of the denominator, is bigger than the degree or the highest power of the numerator. Okay, so the first possibility is the degree of the denominator is larger. Okay, that's how I'm going to summarize it. So the first possible thing that you could encounter when you're doing your homework or when you're on the test in this class is you could be given a rational function where the degree of the denominator is larger. Well, when that happens, so for instance, my first example right here, f of x is equal to x plus 1 in the top, x squared minus x minus 6 in the bottom. Notice, what's the highest power on the x in the numerator? 1. What's the highest power on the x in the denominator? 2. So this is the case. This is possibility number 1. I'm just going to put a little number 1 right there. It's possibility number 1. The degree of the denominator is larger. So what's happening here is, since we're squaring, the denominator is going to grow much faster than the numerator is. So since you're going to be dividing by a number that's bigger and bigger and bigger, when your denominator has the biggest degree, the horizontal asymptote is always going to be the x-axis, or the line y equals 0. You don't have to do any calculations, you just know it. Okay. So the horizontal asymptote, let me abbreviate that with very cleverly, h period a period, the ha is y equal to 0. Okay, so of those other 5 examples, one other of them meets the criteria. I don't want you to shout it out yet. I'm going to give you 5 seconds. Just want you to put your pencil on which other example has the degree of the denominator is bigger than the numerator. And which one is it? The very next one. Yes, this also is the situation number 1. Can everybody tell why that's situation number 1? Is anyone struggling with that particular bit of trivia? Okay, then real quick, here's another 5 seconds. Write down what the horizontal asymptote of that is. All right, so the degree of the numerator in this one, in case you just didn't see and you're being silent because you're embarrassed, which I don't know why that would be, the degree of the numerator is 3. That's the highest power. The degree of the denominator is 5. That's the highest power. That's why this is situation number 1. And the horizontal asymptote is y equal to 0. It's the x-axis. So far, so good. We doing okay? The other situation that you're going to encounter is number 2. The degrees are equal. Now you might be thinking, well, hey, Perkster, what happens if the degree of the numerator is more? And that is fascinating. You don't get a horizontal asymptote, you get what's called an oblique asymptote, you get a line. That's a little pre-calculus. I wish we had a whole semester to talk about rational functions. They're so exciting, but alas, we're not going to do that in this class. Okay, so you're only responsible in this class for horizontal asymptotes. I will not give you any of the other option. Okay, when the degrees are equal, here's how you figure out the horizontal asymptote. So here's my example right here. This is situation number 2. Notice my degrees are equal. I've got a degree of 2 in the top. I've got a degree of 2 in the bottom. Then the horizontal asymptote becomes this. Y equals, and what you do is you take the ratio of the coefficients of those highest powers. So for instance, the coefficient of the top is 3. The coefficient of the highest power is 1 in the bottom. So the horizontal asymptote is 3 over 1, which is 3. Y equals 3. Does anyone not see where I got the 3 in the numerator and the 1 in the denominator from? It's a big question. All right, then please take just a moment. I'm going to give you 20 seconds. Please determine what the horizontal asymptote of just the next one. You don't have to do any more than the next one. We'll do them one at a time. Make sure we're getting caught up with finding these horizontal asymptotes. All right, so again, this is situation number 2. I'm just going to put a little number 2 there for your notes when you look back later. The highest power is 2 in both the numerator and denominator. So when I go to find my horizontal asymptote, what's the coefficient that I'm going to use in the top? Perfect. The number in front of the squared in the top is -1. What's the coefficient that I'm going to use in the bottom? The number in front of the squared in the bottom is a +1. So the horizontal asymptote will be the y value -1. And we'll just draw a dotted line when we go and we graph something like that. Okay, we'll try the next one. X plus 2 divided by x minus 3. Again, this is situation number 2. The highest power in the numerator and denominator is a 1. So my horizontal asymptote is going to be y equals, well, what's the coefficient from the top that I'm going to use? A 1. What's the coefficient from the bottom I'm going to use? A 1. Not a super interesting problem, but it's important that we identify that. So the horizontal asymptote is y equal to 1. So one more. Please do the last one. Identify what the horizontal asymptote is for the last problem. So last but not least, this is another situation number 2. And so the horizontal asymptote is going to be y equals, what's the coefficient from the top? A 1. Great. What's the coefficient from the bottom? Great. Excellent. So vertical asymptotes. Vertical asymptotes happen when the denominator is 0. Horizontal asymptotes are related to the degree of the numerator and denominator. And there's only 2 situations you're responsible for. Okay, so if I gave you something to graph, you are probably half done with the problem. You're probably done with the hardest part of the problem. So the steps to graph a rational function. So if our rational function is not in the format of one of our 2 basic graphs that we saw, and we practiced graphing those last time, then it takes a little more effort. So the way we're going to do it is the following. So the first step, step number 1, you already know how to do. We're going to find the vertical asymptotes. When you find the vertical asymptotes, in parentheses, I'm just going to say you've also found the domain. Those are a related step. So when you do your homework, or in a minute when we turn the page, first thing, when I say graph this rational function, step one, find the vertical asymptotes. Boom. Second step, find the horizontal asymptotes. And again, I just want to emphasize this. The reason we do that, because we're just trying a sketch. These are not going to be perfect graphs because rational functions have a bunch of detail that we're not going to be able to get in because we just have today to talk about doing it, unfortunately. The asymptotes tell you the behavior of the graph. Okay? So they basically sketch an outline of what's happening to this graph. But we need a little bit more detail when we're in by the x-axis and a y-axis. So here are the other things you're going to do. You're going to find the y-intercept. And in case you don't remember from your intermediate algebra, the way you find the y-intercept, meaning where does the graph go through the y-axis, is you plug in x equal to 0. The y-axis is at the x value 0, so you plug in the x value 0 to figure out where does the graph. So what I'm just trying to do is I'm just trying to give you a few really quick and easy things that you can do to get a little bit of a clearer picture of what's going on. The next thing you're going to do is you're going to find the x-intercept. Meaning, where does the graph go through the x-axis? And again, in case you don't remember your intermediate algebra about where that happens, the x-intercept happens when the function is equal to 0. Whereas I told you that a graph never, ever, ever, under any circumstances, goes through a vertical asymptote, there are situations where the graph might go through the horizontal asymptote right around the origin. Horizontal asymptotes tell you the long-term behaviors. You get farther and farther away from the origin. Okay, so what the next thing you're going to do, and I'll show you how to do this in a minute, you're going to answer the question, does the graph go through the horizontal asymptote? And then last but not least, just to make sure that we have the proper scale, if you need another point or two, what you're just going to do is you're going to plug in a couple other points. So you're just going to plug in any needed x values. Depending on the problem, you might not need to plug anything in. You might be good to go. You might have a problem where you need to plug in 2 or 3 things. Just depends. You're going to use any points you plug in along with the horizontal and vertical asymptotes to just draw a sketch. That's all we're doing is a sketch to get a very generic picture of the behavior. All right, so I'm going to work this example along with you. We're going to do these problems together just to get the experience of graphing these. So this first one, we've already done, in fact, the first 2 steps. So my example, I'm lazy, I saved myself a little work. Step number 1 is what's the vertical asymptote? Okay, that's always going to be step number 1. So I'm just going to flip back to the front page. This is x minus 1 over x plus 4. That was the very first problem we did, so it just saves us a little time. The vertical asymptote we found last time was the x value negative 4. Okay, if you weren't here last time, that's at the very end of our video from last time, so you can watch the very end. So the vertical asymptote is the x value negative 4. So I'm going to draw a nice dotted vertical line, and this tells me the graph's never going to go through this. So here we go. Dot, 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 dot. Very satisfying. There it is. If at any point you encounter a question, please do not hesitate. I know this is difficult stuff. Okay, so this is one of the most difficult sections in the book, in my opinion. Okay, is this graphing these rational functions. Not that you can't do it, it's just tough. All right, the second thing we're going to do is we're going to find the horizontal asymptote, which again, I believe, if I'm remembering right, we've already done. No, we haven't. We did one like it, but we didn't do this one. Okay, so is this the situation where the degree of the denominator is larger or the degrees are equal? The degrees are equal. Okay, so that means my horizontal asymptote is going to be the ratio of the coefficients. So what's the coefficient that I'm going to use from the top? Okay, 1. What's the coefficient from the bottom? 1. So not super interesting, but we don't want this first one to be super interesting. So I'm going to make a dotted line horizontally at the y value 1. We okay so far? So this tells me a lot about the graph. Okay, it tells me that depending on where the points I find are, like when I get close to the vertical asymptote, it's either going to be going up or it's going to be going down. It just depends because the asymptotes define the behavior of the graph. So those two things there tell me a whole lot. Now what I just need is I need a couple points to help me understand what the scale of this graph is. So the third thing we're going to do is we're going to find the y-intercept. The y-intercept is what you get when you plug in the x value 0. So I'm going to plug in 0. So I'm going to write f of 0 right here. So when I do that in the numerator, I get 0 minus 1. In the bottom, I have 0 plus 4. That is negative 1/4, or if you're fond of decimals, that's negative 0.25. So at the x value 0, I'm at negative 0.25. So I'm right around here. The fourth thing is I'm going to find the x-intercept. The x-intercept is when the function equals 0. Now, here's a nice thing about, probably the one nice thing about dealing with a rational function. The only time a fraction is going to be 0 is when the top's 0. So I don't have to worry about the denominator in this case. So when you find the x-intercept and we let the function equal to 0, so let me just write that down first. Here's the function equal to 0, x minus 1 over x plus 4 is equal to 0. But here's the thing, the denominator doesn't impact that at all. So all I have to worry about, I'm just going to draw a little arrow, all I have to worry about is when is x minus 1 equal to 0. And that happens at the x value 1. So at the x value 1, it goes through the x-axis, so 1, 0, so right there. So technically, I could draw a sketch. It wouldn't be perfect. I can draw a sketch now of the right half of this graph. I've got the asymptotes. I've got a couple points that it goes through. We're good to go. But before we do that, we're going to answer this question, and then we'll be ready to finish this problem up. Remember, this question is, does it go through the horizontal asymptote? So here's how you do this. Okay, so you're going to take your function, x minus 1 over x plus 4, and you're going to say, does this ever take on the value of the horizontal asymptote? So I'm going to look back up. The value of my horizontal asymptote is 1. So I want to know, does this ever have the y value 1? Now, here's where your intermediate algebra will help you. I apologize because the sections, I believe, in our textbook are out of order because now you're expected to know how to solve a rational equation. And while it's technically review from the previous class, it's still a tough thing, and I would rather have had the time to talk about it. So remember, here's all I need you to remember at this point. When we come back next week, or maybe it's next class, I don't remember. When we come back sometime in the future, we'll talk about solving equations. All I'm going to do is multiply by the common denominator on both sides. And so what that means is I'm going to multiply both sides by x plus 4. Maybe this looks familiar to you. Maybe it doesn't. We'll talk about it in more detail again. So then what happens on the left is the x plus 4s cancel, and I'm left with x minus 1. On the right, 1 times x plus 4 is x plus 4. I'm going to go ahead and solve this. I like to bring my x's over to the left. You know that about me. We've been knowing each other for 7.5 weeks now. So I'm going to subtract the x, and then here's what I get. And here's how I'm going to draw my conclusion. When I go to put all the x's on the left, what happens to the x's on both sides of this equation? They both cancel. So what this tells me is this is a contradiction. If you remember when we did this on our first day of class, okay, I'm going to write that down. You don't ever have to write that down, but I'm just letting you know, I'm giving you the detail here. Since that's a contradiction, what that means is no, it doesn't go through the horizontal asymptote. If you get an X value there, which I think one of my examples, it's going to happen. If you get an X value there, that tells you right where the graph's going to go through the horizontal asymptote. And that'll be the only point you have to worry about. So this one does not. Okay, so at this point, and I know you're not super comfortable doing this. This is the very first one, but at this point, you plug in 2 or 3 or 4 or 100 values until you get pretty comfortable with what this looks like. So here's what I'm going to do. I'm just going to do 2 values. I'm going to plug in a value right in here, and then I'm going to plug in a value over here. So a value here, I'm going to do -2. So I'm going to plug in the function at -2. Let me slide over here so you can actually see the work. Yeah. Yep. I just want to see what the scale of the graph is. What are a couple points that it goes through, and then I'm going to use any points that I have along with the fact that it's not going to go through the horizontal or vertical asymptote, and I'm just going to draw a little sketch. That's all. This is not going to be a perfect graph. I would not use this to make any predictions, but all I want to see is, do you understand the shape? Do you understand what the asymptotes are telling you about the graph? That's what you're telling me when you do this. Okay. So I'm going to plug in -2. When I do that, I get -2 minus 1 in the top. In the denominator, I get -2 plus 4. So that's -3 over 2 or -1.5. So at -2, I go down 1.5. And so now I have more than enough. I didn't do that point for me. I did that for you because I just want you to understand the process. So now I'm going to use these points that I have along with the fact that the graph's not going through these asymptotes to finish the sketch. So the sketch is going to look like this. Whee! It's going to go in that direction and squeeze, just like that. There we go. Going to get closer and closer and closer to those asymptotes. It's not going to go through either of them. And so that tells me the shape of the graph. I'm just going to do 1 point on the left for time's sake. If when you're doing your homework, if you feel like you would need to do another one, that's great. I'm going to put in, let's say, let's see, this is at -4. Let's put in -6 just for kicks. So here we go. The function value at -6. In the top, I'm going to have -6 minus 1. In the bottom, I'm going to have -6 plus 4. That's -7 over -2, or 3.5. So at -6, I'm going to go up 3.5. So -6, so here we are, and then 1, 2, 3.5. Again, if you feel like you need to put another point in, that's great, go for it. But now I have all the information I need. I know where the graph's going to be. I know the asymptotes, so I know what's going to define the behavior of the graph. So I'm just going to do this. I'm going to woo-hoo-hoo that way, and then that way. And there we go. It's just a sketch. Boom, done. That's all I want. And you're thinking, that's all, that's a lot. It is a lot, you're right. But that I don't want any more. I could ask for other things, believe it or not, but that's all I want at this point in your math lives. Okay, so I'm going to try to leave this here for a moment or two. You can look down at the next problem, and I'm going to give you 4 or 5 minutes to go through as much of the process as you can get through in 4 or 5 minutes. If you need anything from me, raise your hand. I need a little exercise. I'll come around and say hello, and you can ask me whatever questions you need. I want you to feel good about this. If you're watching on the video, I'm going to push pause to make the video a little shorter. So you should push pause too. Let's see how much you got through. If you didn't quite get all the way, I totally understand. I just have a certain number of problems I need to get through. So we're gonna start with this one. Okay, so first thing, the vertical asymptote. The vertical asymptote happens when the denominator is 0. You could have looked on page 1. We did this last time. So when x minus 3 equals 0, that happens, the vertical asymptote happens at the x value 3. If you got something different than me, please don't be shy. Raise your hand. If I don't see any hands, I'm just going to keep moving along. I don't want to bore you to death either. Okay, so there's my vertical asymptote. My number 2, my horizontal asymptote. I think we did this one already, so it's also on page 1. But in case you didn't notice that, this is the situation where the degrees are equal. It's the same situation as the previous problem. So we're going to use the coefficients 1 over 1. So the horizontal asymptote is 1. So just like the previous problem, there is my horizontal asymptote. Not too bad. The hand looks pretty steady today. We're doing all right. Okay, so thing 3, these are the new things that we didn't do on page 1. Thing 3 is where is the y-intercept. So that means I'm going to plug in 0 in the function. So 0 plus 2 in the top, 0 minus 3 in the bottom. So that's negative 2/3. So at the x value 0, I go down 2/3. So right about there. Again, you have all the information you need to draw a sketch, because that's all we're drawing is a quick little sketch. But let's keep going. Next, we'll do the x-intercept. That happens when the function itself is equal to 0. And I mentioned to you that really all you got to worry about is the numerator. So I'm going to worry about the x plus 2 being equal to 0, and that happens at negative 2. So at negative 2, that's where the graph goes through the x-axis. Before I draw the left-hand side, okay, I know you want to, I want to, but before we do that, we got to answer the question, does the graph go through the horizontal asymptote? Okay, so this first one I gave you very similar to the previous one. We've got x plus 2 over x minus 3. Does that ever take on this dotted value right here? So does it ever equal the y value 1? So like last problem, all I need you to know about solving a rational equation right now is that we're going to multiply by the common denominator, and there's only one denominator, so we're okay. So on the left, I have x plus 2. On the right, I have 1 times x minus 3. And when I go to get all of my x's on the left by subtracting, I see the same thing happen here as happened in the previous example. I end up with a contradiction. So since that's a contradiction, 2 is never equal to negative 3, then I can answer definitively no. This does not go through the horizontal asymptote. So now I'm ready. Well, I'm going to just go ahead and graph the left. If you found another point on the left, that's fine. That's your prerogative. I want you to be confident. I'm not going to, so my sketch is just going to look like this. On the right, I'm going to get one value. It doesn't matter what you picked. I'm going to pick 5. I have no secret reason for picking 5 other than it's to the right of the asymptote, and it's a little bit, it's a couple units away to give me a little bit of space there, but there's no reason other than that. So in the top, that's 5 plus 2. In the bottom, that's 5 minus 3. That's 7 over 2, or 3.5. So at the value 5, I go up 1, 2, 3.5. And again, that's good enough for me. If you want to get another value to kind of see how it swoops out, I understand. But this is what the graph is going to look like, something to this effect right here. And there we go. Before we move on to the next example, we're going to work through the next one together. Does anyone have a question, comment, or concern? Okay, I'm trusting you to tell me. I've already told you I think this is difficult stuff, so I'm not trying to rush through this at all. Okay, so here's the next one. So step 1 on the next problem, this is the top of page 3. Step 1 is what are the vertical asymptotes? Well, we're just to save a little time on this example. We've already done this on page 1. What are the vertical asymptotes of this one from page 1? -2 and 3. Perfect. There's 2 vertical asymptotes. So I'm going to make 2 vertical lines. So again, if you're watching on the video, or if you weren't here last time, we did this when we went through the examples. I put this as one of the examples to save us a little time later on. So I've got a vertical asymptote at -2, and then I've got a vertical asymptote at 3. Okay, step 2, the horizontal asymptotes. So once again, this is one of the examples we did at the beginning of class today. So if you go back to page 1, what is the horizontal asymptote of this problem? 0. In fact, you probably didn't even need to turn back to page 1. This is the situation where the degree of the denominator is more. And so when the degree of the denominator is more, we got y equals 0. So that's just the x-axis. I'm going to try not to make this too dark because I don't want to muck up the graph here, but we're just going to put a nice little dotted line there. Okay, good. We got a lot of information. Step 3. I'm going to find the x-intercept. I'm going to find the y-intercept. I'm going to plug in the x value 0. And when I do that, the top is 0 plus 1. The bottom is 0 minus 6. So that's negative 1/6. They're just a wee little bit. The fourth thing, the x-intercept. The x-intercept, I set the function equal to 0. So I'll write that out. But the nice thing about setting the function equal to 0 is a fraction's only ever 0 when the numerator is 0. So I only have to worry about the numerator. That's good because I don't want to have to worry about the denominator at this point. And so that makes it x equal to negative 1. Now we can see from what we just did on the graph that the answer to question 5 is yes, this one does go through the horizontal asymptote. But I'm going to go through the work because I want to make sure it doesn't happen anywhere else. So I'm going to take the x plus 1 over the x squared minus x minus 6. Does that equal my horizontal asymptote? Well, this time the horizontal asymptote is 0. Oh, well, we can see I just mentioned to you that the only time a fraction is going to be equal to 0 is when the denominator is 0. We just did that. Okay, so I'm just gonna draw a little arrow. How about some eyeballs? There we go. Just look up there. We've already done the work for that. Okay, so I'm not going to waste your time and do the work again. So it does go through the horizontal asymptote, but it only goes through the horizontal asymptote there. There's no other places. So yes, at x equal to negative 1. So here's the thing. You might not think by looking at the graph that we have a whole lot done for us, but the truth is we really do. So we know that on the wings here, on the very far left, the very far right, once I know if it's above or below the x-axis, the asymptotes define the behavior. And then in the middle, you know more than you think you do, and I'll tell you about that in just a minute. Okay, so the sixth thing is I'm just going to plug in some points. So I'm going to plug in a point. I'm just going to go left to right. So I'm going to start here at the left. I'm going to put in the point. Let's do negative 4. Again, I have no secret reason other than it's to the left of the vertical asymptote, and it gives me a little buffer room just to see what's going on. So I'm going to plug in negative 4. And when I plug in negative 4, the top is negative 4 plus 1. The bottom is negative 4 squared, which is 16, minus negative 4, which is plus 4, and then minus 6. So that's negative 3 over 14. So you can use your calculator, but negative 3 over 14 is below the axis. That's really all I care about right there, because it's a negative number. And okay, great. You can get more points if you want. I don't want. I want to do the minimum amount of work possible, which I'm pretty sure is probably your theory on this too. And so there we go. I can sketch out. Given that point is below the x-axis, and given that the asymptotes are going to define the behavior of the graph, I'm just going to draw a curve that approaches both those asymptotes. I'm going to skip the middle part. We're going to go over on the right part. I'm going to pick a point over here. I'm going to pick the point 5. Again, no secret reason. So the function value at 5 So the function value at 5 and the top is going to be 5 plus 1. In the bottom, I've got 5 squared is 25 minus 5 minus 6. So that's 6 over 14. Again, it's just a little bitty bit. It's like about a half, but it's positive. That's the key part that I care about. So at 5, I go up about a half. So again, what does that tell me? That tells me that since it's above the x-axis, and since the asymptotes define the behavior of the graph, that here's what my graph is going to look something like. I kind of missed the point, but because I was talking and I can't talk and draw, but you see what's going on there. And so all that remains is the middle. Well, here's what you know about the middle. You know that the graph goes through the asymptote here, and it never goes through it anywhere else. So it never loops back or anything like that. So what I know so far is that the graph's going to do something like this. Okay? Because it goes through the asymptote, it never comes back around. So just what I want to know is I'm just going to get a point over in here to see how far does it swoop, what's it doing over here, and then we'll be about done. So I'm going to plug in the value 2 or 1. Either of those would be great, but I'm going to use 2. So when I plug in 2, in the top 2 plus 1 is 3. In the bottom, 2 squared is 4 minus 2 minus 6. That's 5 over negative 4, or negative 1.25. I don't know why I put 2 plus 3 in the top. It's not really 5. It should be 2 plus 1. I think I was adding them in my head while I was writing it down. So good job, Perkster. Appreciate that. So it's negative 3 over 4, not negative 5 over 4. Sorry. So that's 2, negative 3 over 4. So here's what I can see is I've got this point, I've got this point. Here's where it goes through the axis. So I'm just going to connect them. The asymptotes define the behavior of the graph. A graph never goes through that vertical asymptote. So that is that's approximately what that graph is going to look like. If it went through the vertical asymptote again, it is possible for the graph to curl up again and be like a little mini parabola inside there. And I think that's kind of what your next one's going to be. So here's what I would like you to do, because I know that this is complicated stuff. I want you to do steps 1 through 5 of the next one. And then once we're there, I'm going to give you 3 or 4 minutes to do steps 1 through 5 of this one. And then once we see what we have, we'll get a few points to finish off what's going on. I don't think we did anything with this particular function on page 1, so all of this is fresh and new. I'm just going to catch you up to where I am, and then we're going to finish this gradually, and then you're going to ask whatever questions you have to. Again, this is difficult stuff, so if you have any questions, that would be a totally normal thing. So just to catch you up, the vertical asymptotes happen where the denominator is equal to 0, so x squared minus 9. That's nice and factorable. You will find I'm very kind and loving. Your denominator will always factor. I'm asking you to graph because I do not want any decimals or any crazy stuff like that. So x plus 3, x minus 3. So I have two vertical asymptotes, one at -3, one at +3. You can see them on my graph. The horizontal asymptote, we've got the situation here where the degrees are equal. So my horizontal asymptote is the ratio of the coefficients. So the coefficient in front of the x squared in the top is 1. The coefficient in front of the x squared in the bottom is 1. So I've got y equal to 1. You can see that reflected on my graph. So far, we so good. Any concerns yet? Okay, the next one, I'm going to find the y-intercept. The y-intercept happens when x equals 0. So I plugged 0 in and got 0 squared on the top over 0 squared minus 9 on the bottom. So that's 0 divided by -9, or 0. So that's the origin. I put a nice red dot right there in the middle. The x-intercept is where the fraction equals 0. So x squared over x minus 9 equals 0. Well, that reduces to just when the numerator is equal to 0. So the square root of both sides here is x equal to 0. It's the same point we already got. It's 0, 0. There's no other x-intercepts on this graph. So that tells me something right there. It never goes through the x-axis ever again. And then the last thing is, does this go through the horizontal asymptote? Does this go through the y value 1 that I have dotted? And you can see when I set this equal to 1, and I clear the fractions by multiplying both sides by x squared minus 9, I end up with the equation x squared equals x squared minus 9. When I go to get my x squareds all on the same side, I get a contradiction. So no, it never goes through. So even though there's not a lot on the graph right now, I know a lot of things. I know that this never goes through the x-axis again. I know it never goes through the horizontal asymptote again. So those asymptotes are going to clearly define my behavior. So we're going to do this in 3 steps. Step 1, I'm going to give you a minute. I want you to pick any x value over here to the left. And I want you to plug in an x value over here, and I want you to then sketch what's happening on the left part of this graph. Okay, so here goes. I'm going to pick the value. Again, I have no reason for this. All of our conclusions should be the same. I'm going to pick the value -5. And so when I plug -5 in the top, -5 squared is 25. In the denominator, -5 squared is 25 minus 9. So that is 25 over 16. That's 1 point something. Okay, so I'm going to come over here at -5, and I'm going to go up 1 point something. So 1, and then somewhere right about here. Okay, well, again, that tells me everything I need to know. I've got both a vertical and a horizontal asymptote this graph is never going to go through. I know that the graph is right there above the horizontal asymptote, so it's just going to look something like this. A nice curve that is going to go toward those asymptotes. Anybody got a problem sketching that part of the graph? Anything that you need, any advice you need? Okay, well then let's continue. What I would like you to do, we'll come back to the middle. I'd like you to pick a point over here on the right side and do the same thing for me. Okay, so once again, it does not matter. I didn't give you specifics. I'm going to pick the value 5. Now, if you're super clever, you could say, hey, Perkster, this is an even function. So you're going to get 25 over 16. If you saw that, then awesome. I'm proud of you. If not, then you plug something in. 5 squared is 25 in the top. And then in the bottom, 5 squared is 25 minus 9 in the bottom. And once again, I get 25 over 16. So 1 point something. So I'm going to come over here at the x value 5. I'm going to go up 1 point something. So 1 point something, somewhere right about there. So the graph's going to look something like this. Just a nice slow roll right through that point on both sides. Again, we're just drawing a sketch. It's not perfect. I wouldn't use this to calculate and predict values, but you're telling me that you know what's going on. Now in the middle, we have enough information to graph this, because we know that it's not going through the horizontal asymptote, so it can't point up, so it has to point down. But just so that we're all clear and nice and settled, go ahead and use the fact that this is even and pick a value either on the left or right, and then complete the graph in the middle. I'm going to put in 2. If you want to put in the same thing, if you want to be just like me, because why wouldn't you, then I'm going to put in 2. So when I plug in 2 in the numerator, I get 2 squared, which is 4. In the bottom, I get 2 squared, which is 4 minus 9. So that's 4 over negative 5, or negative 0.8. So I go over 2, and I go over 2 and down 0.8. So somewhere right about there. Since this is even, or if you don't believe me, you can plug in negative 2. The same thing's going to happen over here. And so here's what's going on with this graph. I'm just going to get like sort of a little parabola looking thing here in the middle that's going to go down to those asymptotes, and the graph never goes through the asymptotes, so it just looks like that. In this class, those are pretty much the 2 things that you're going to encounter. We don't have a lot of time to go into other fun details. Okay, so I've got one more thing I need to clue you in on that you might encounter on your homework or test. So once you finish drawing that graph, we're going to go to the last page. So the last couple problems, we are going to graph things. In fact, we're going to graph one of the things, and we're just going to get the other one into the point where we could graph it, because that's what we're going to have time for. We're going to graph things that are not in lowest terms. Okay, so again, this relies on a little bit of intermediate algebra knowledge. This part we are not going to review. So do me this favor, I'm going to give you 30 seconds. I want you to factor the numerator of that and write that expression, write that function in lowest terms, please. Okay, so when I factor the top, it's just a cute little difference of squares. X squared minus 4 factors to x plus 2 at times x minus 2. The denominator is x minus 2. And notice that I can cancel out the x minus 2's there. So I will do that. And so then I'm just left with x plus 2. So this graph turns out not even to be a fraction anymore. It's just a linear function. There's 2 things I've got to tell you about here. When you encounter something that's not in lowest terms, that you can remove a factor, what this is called, okay, what this right here is called is a removable, which I don't know that I can spell, remove, R-E-M-O-V, A-B-L-E. Is that how you spell removable? I don't know. Discontinuity. I can spell discontinuity. Okay, so it's called a removable discontinuity. I'm going to leave it to you to spell removable properly on your paper. So what that means is there's actually a problem here. What's the x value that this is undefined for in the bottom? 2, right? 2 minus 2 in the bottom is going to be 0. Okay, so there's a problem at x equal to 2, but it's not a vertical asymptote this time because I could remove it. Okay, that's the difference in this problem than previous ones, is I can remove this discontinuity. So here's what you do when you have something that you can remove. What we're going to do is we are going to graph this, and then you are going to put a hole at the x value, whatever it is, x value 2. So we're going to start with the hole, and then we'll just graph the rest of this around it. So I'm going to put in the x value 2 into this. When I put 2, 2 plus 2 is 4. So I'm going to go over 2. I'm going to go up 4. I'm not going to make a dot, though. I'm going to make a hole. What that hole represents is in the original function, that actually the x value 2 is undefined. Okay, x value 2 in this original function is undefined, but I was able to remove that. And now the rest of the graph is just the line x plus 2. So this line here has a slope of 1 and then a y-intercept of 2. So I'm going to make my y-intercept of 2. I'm going to put a dot there. The slope 1 means I go up 1 and over 1. So up 1 over 1, up 1. Don't put a dot in the hole. Up 1 over 1, up 1 over 1, up 1 over 1. So the rest of the graph is just a line like this. Yeah. Because I took the x value 2. This isn't the y-intercept. I took the x value 2. That's where it's undefined here, right? Would you agree with that? It's undefined. Does everyone see that in the original function at x equal to 2, I have an undefined value? You with me on that? So because of that, something special's happening there. So at the x value 2, I plugged 2 in. 2 plus 2 gives me 4. And that's where I got that from. That's why I put the hole at 4. The x minus 2's cancel out. That's why it's called a removable discontinuity. I removed the point of discontinuity, right? I crossed it out. That x minus 2 that created the undefined value in the bottom, I was able to remove it. That's why it's called a removable discontinuity. So the last thing we're going to do is I want you to take a moment. I'm going to give you we've got 4 minutes. I'm going to give you one of that to write this as a reduced fraction. And then I'm going to tell you what to do with the graph if we had had time to graph it. You know what to do with almost all of it. All right, so I gave you your minute. The numerator is x squared minus 1. That factors to x plus 1 times x minus 1. The denominator, this trinomial, the two factors of -2 that add up to -1 are -2 plus 1. So notice, there's two places that there's a problem in this original function. Okay, there's a problem at the x value 2. There's a problem at the x value -1. But here's the thing, I can remove one of those. Which one can I remove? The x plus 1 cancels out. So if we had time, and you might practice with this, if we had time, we would graph this function, x minus 1 in the top and x minus 2 in the bottom. You would graph it fully normal. The only thing that you would do any different than anything we did, you're still going to have a vertical asymptote at 2. You're going to have a hole at the x value -1. It's not a vertical asymptote because we removed it. So you'd put a hole there. Yeah. When you plug it in, what I would do is I'd plug is this the question? I plug the -1 in here and you'd get -2 over -3. Is that what you're asking? So this factored here, x squared is x and x, unless I did it wrong, which is always possible. The two factors of -2 that add to -1 are -2 and +1. So since that's an x plus 1, when I subtract 1 from both sides, I get the x value is -1. Is that your question? Okay, yeah, so the x value has to be -1. If this was an x minus 1 in the bottom, then you're right, it would be a 1 right here. But the reason it's not, these can't have the same sign because this is a -2 when I go to factor. So you would still put a vertical asymptote at the x value 2. You'd have a hole at the x value -1, but all the rest of the graph would just be this right here, which we graphed something super similar. In fact, two things super similar to that in this class.